Hello, welcome to this lecture on the binary world. My name is Dr. Richesh Shujuda. In this lecture, we will be looking at binary values in number systems. This is chapter 2 of the textbook. So I suggest reading the textbook, reading chapter 2 before watching this lecture. But you could do it either way, as long as you do use the textbook as a resource. So at the heart of computing systems is this idea of a dichotomy. A dichotomy is two states. It can be high or low. These states have nothing to do with each other. In logic, you can have true or false, often represented as capital T for true or capital F for false. In electrical circuits, you can have low current and high current. You can have a lamp which switches on or off. You can have in a circuit current flow or no current flow. Obviously, the implication of the current flow or no current flow will determine whether the lamp is on or off. In polarity, you can have positive orientation, negative orientation. In binary, which is what we are interested in this, which is the core of what we're doing in this lesson, is this notion of a two-valued state, which is a 0 or 1. So from the beginning of your schooling, I assume in grade 1 or 2, you learned about the number system. A very special, or as you would find out after this lecture, a very not so special number system called base 10. And in grade 1, your teachers would have taught you to count from 0 to 9, from 0 to 10. Or in this number system, there were always 10 symbols. Okay, so what were these symbols? There was 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. These were the numbers, these were the symbols that made up this base 10 number system. So we have to always ask ourselves why. So why are there 10 symbols? Where does this number system come from? Where do these symbols come from? Okay, the 6 and the 4 and the 2. I mean, these aren't letters. What are they? But the most importantly, we ask ourselves, what is this number system and what is it representing? So we find that the base 10 number system is representing configurations of these different digits from this alphabet that has 10 things. Okay, the 10 symbols, as I said, is 0 to 9. And in these 10 symbols, if you take them and arrange them, you can get many different numbers, and there are infinitely many numbers. So we've got the number, for example, 642. 642 is a number in base 10. And in this base 10 number, we've got 600 ones plus 40 ones plus 2 ones, and all of that gives us a number in base 10, which is 642. We could have easily had, in place of 6, we could have had 7, which is also a symbol represented in the space system. We could have had 9, which is a symbol represented in the space system. 2, we could have had, in place of 4, you could have had a 3. In place of 2, you could have had a 1, and so on. And no matter what the number was, it would be represented as different positions. So let's have a look at what these positions are. So this position is called the unit position. This is where the 2 is. Obviously, we could have had a 1 here, a 6 here, and any other number from these 10 symbols. But in this case, we have a 2. The position after this, at position 2, we have a 4. The 4 could have been a 6, it could have been a 9, and so on, right? So in this case, it's 4, and because of the position being position 2, it's 40. In position 3, we have the number 6, and the number 6 here is at the 3rd position, which means that it's the 100th position. And in the 100th position, you express it with 2 zeros. In the 10th position, you express it with 1 0. And in the 2 position, you express it with no zeros. So let's try to, using the positions, let's try to express this number. So this number can be expressed as 600, okay, plus 40 plus 2. That's 6 hundreds, 4 tens, and 2 ones. We can use scientific notation as well by just saying 60 multiplied by 10 to the power of 2 plus 4 multiplied by 10 to the power of 1 plus 2 multiplied by 10 to the power of 0. Let me just repeat. The positions associated with the numbers here is 1 for 2, 2 for 4, and 3 for 6. So this is if we were to count in tens. So assume that, well, suppose that we didn't have 10 symbols. We had only 8 symbols. If we had 8 symbols, then we would be in a situation where 6 would only be able to be replaced with 7 other things. Okay, in total 8 things altogether. You could take the position where 6 is. You could have 8 things taking 4's position. You could have 8 things taking 2's position. This is if we were counting in 8s. So that means that the values, if we're counting in 8s, there are 8 things in the representation, which means that we have 0, 1, 2, 3, 4, 5, 6, and 7. These are the 8 things in our representation, which means that you couldn't have the number 9 in here because it's not part of the representation. You couldn't have the number 8 in here because it's not part of the representation. Instead, the numbers from 0 to 7 could be represented. So all of these numbers are in that range. You can see that. The 6 is in that range, the 4 is in that range, the 2 is in that range. If we were to be counting in 8s, that means that you could have 6, right? The position 3, 6 multiplied by 8 different things that could take that position to the power of 2. Why 2? Because it becomes minus 1 the position. So if the position is 3, then this would be 2. If the position is 1, then the exponent will be 0. If the position is 5, then the exponent will be 4. So it would be 6 multiplied by 8 to the power of 2 plus 4 multiplied by 8 to the power of 1 plus 2 multiplied by 8 to the power of 0. And anything to the power of 0 is 1, as you all know. Anything to the power of 0 is 1, not 0. Okay, so that means that this number here can be represented as a number in base 10 if it is in base 8 in this way. So if this was a base 8 number, 6 for 2, if it was a base 8 number, that means that there are only 8 things, 8 different symbols that can make up this number. Then we can represent it in this way to convert it to base 10. So if you multiply this out and add it up, you'll get the number 418, which is a number in base 10. Okay. I hope that made sense, because this is a very important thing to understand in these next 2 lectures. Right, so let's move on. So just looking at this in a bit more detail, you've got the positional notation. Okay, this is now just fleshed out. It looks very simple. It looks like primary school mathematics, but it's the understanding that I'm after here. Okay, so every computer scientist knows how to speak this language. Every computer scientist knows what it means to be in a particular base. It's part of the basic, that's why this course is called Basic Computer Organization. This is the basics. Every computer scientist needs to know these things. So the number 642 in base 10, right? 10's positional notation, okay? We can represent it as using scientific notation. 6 multiplied by 10 to the 2, because the third position, okay, which is 6 in this case, it becomes 3 minus 1, which is 2, the exponent. Okay, that's the same thing as saying 6 multiplied by 100, which is 600. And we add that to 4 multiplied by 10 to the power of 1. Why 1? Because 4 is at position 2. And we just simply say 2 minus 1 to get us the exponent. You just subtract 1. And we can generalize this. I'm sure some of you are already thinking about how are we going to generalize this. And you'll find there is a very simple way of doing that, which becomes 40 multiplied by 10, which is 40. 4 multiplied by 10, which is 40. Plus 2 multiplied by 10 to the power of 0. Right? 0 in this case will make this 1. Okay, so that's 2 multiplied by 1, which is 2. And this number is then, if you're counting in tens, then this would be the number. It's the number itself, represented as a number in base 10. So this is what we mean when we say this number is in base 10. It's a number in base 10, which means that our base r, which we can call this value here, is 10, right? If this was a number in base 8, then this would change to 8. If this was a number in base 2, then this will change to 2. This will become 2. If this was a number in base 16, then this would become 16. Okay, but the more observant of you will be thinking to yourself, how can this be a number in base 2? Because it has numbers that are not within the range of between 0 and of 0 or 1. Okay, so this can't be a number in base 2 because it has a 6, and 6 isn't in the alphabet. The only alphabet for base 2 is just the numbers 0 and 1. For base 3, it's 0, 1, and 2. For base 4, it's 0, 1, and 2, 0, 1, 2, 3. For base 5, it's 0, 1, 2, 3, 4. For base 6, it's 0, 1, 2, 3, 4, 5. For base 7, it's 0, 1, 2, 3, 4, 5, 6, and so on. So that's important to remember, because if I ask you, is it possible to represent this number in base 2? You would have to check if all of the digits are within the alphabet of the number. Okay, I hope that makes sense. So like I said, that number 642 can be represented as 6 hundreds and 4 tens and 2 ones. In the representation of this number, it's a representation of it. All right. So the base of a number determines the number of digits and the value of the digit positions. We'll talk about it more in detail, but the main thing here, and something that most of you might be thinking about, is that why have we been indoctrinated with base 10? What is so special about base 10? And you'll find that there is nothing special about base 10. All of the bases have infinite values. All of the bases can do arithmetic. All the different bases can do everything the others can do. And that really means what is special about base 10. And well, then that brings up the question, where did it come from? Where did base 10 come from? Well, there's a lot of debates about that. Some people say that it's because we have 10 fingers. Others say that we all don't use base 10. Some of us use base 2. For example, if you're counting cattle, so say, you might not need a very complicated base system. Maybe base 3 will suffice. You can just make 3 notches in the sand, or 2 notches and a cross in the sand. And you can count it up afterwards. And that'll be your base 3 representation. So there is nothing really special about base 10. It's just a pity that we've been taught that this is the base system to be working with, but like we say, there's nothing special about it. There might be people who don't even use this, or maybe, who knows, if you're very ambitious, maybe some civilizations across the galaxy, they are probably different species who evolved differently from humans, who don't have 10 fingers. Maybe they have 11 fingers, or maybe an even number perhaps, but they use a different base system. That'll be really interesting to find out. But anyways, I digress. So if we are to convert from any base to base 10, then we can use this formula. And this is the formula we've been talking about all along. So as a formula, you can say that where I is the ith position of the number, dn multiplied by the base, dn in this case is the leftmost digit. That's your dn. Multiplied by the base that we're in, right? If this is the leftmost digit, and n is the index of that digit, okay, you start counting from 1 from the right, then it becomes multiplied by the base to the power of n minus 1. Okay, so let me just highlight this. Okay, let's go back up again and let's see this. Okay, so we're going to go back here. This was in the example 642. We were in base 10. So your 6 was position 1, 2, 3. It was position 3. So it becomes 6, which is position 3, multiplied by the base, which was 10, to the power of 2 because it becomes 3 minus 1. Okay, 3 minus 1 because it's 3 minus 1 because this is 3. This will be 3 minus 1. Right, that becomes where our 6 goes. Plus, then we have to find out where our 4 goes. And that becomes your D of n minus 1. Okay, 4's position was 2. So that means that your R, your 10, will be to the power of 1. Okay, plus dot dot dot, and so on. So the number 642, using this formula, as I've shown you, can be represented as 6, which is the third position, multiplied by 10 to the power of 2, plus 4, which is the second position, multiplied by 10 to the power of 1, plus 2, which is the first position, multiplied by 10 to the power of 0. And they omitted it because anything to the power of 0 is 1, so it becomes times 1, which is the number itself. So even though we ignore these numbers at the bottom here, okay, even though we ignore them, okay, we just wrote them in here so you can see it. But you ignore it in obviously the computation. It's just there so you can see it in this formula. You can understand where it comes from. So this is actually a very important formula because if I give you a number and I ask you to convert it to base 10, this is the formula that you're going to be using. Right? You're going to not memorize this. You're going to understand it. You're going to take the time to understand how it's constructed, and the way it's constructed is with the intuition of the previous slides, like this and this. Okay, the intuition of the previous slides, and you can understand this very well because if I ask you to expand this formula, suppose you had the number 642.13. In that case, you would now need to expand this formula so that it can facilitate that radix point as well as the numbers that come to the right of the radix point. Well, we are going to be discussing that anyway, so we'll see how that works out, but you won't be able to get to that unless you understand this formula, not just memorize it. So remember that R is the base, N is the number of digits, I is the position, right, the position of the digit. In this case, your I is, well, it's this 2 and this 1. Your I is n minus 1, your I is this n, and so on. It's your I. And D is the digit, as I've said. Okay. We'll call this formula the positional notation formula. Well, that brings up a fourth problem. So can you show that this representation must always be unique? So more specifically, can you say that if you have a number in base 10, if you represent it using this in this way, will it always give you the same number? Okay, it's it's intuitive, and it's kind of obvious if you think about it. Because any number in this positional notation formula will give you the number itself in the same base, with the same operations in that same base. So if this was base 2, and this positional notation formula was particularly, if it was using base 2 operations, that is base 2 multiplication, base 2 addition, and so on, then you will get the same value in base 2 because it can be represented in that way, and you're counting in the same base. In this case, because we're doing base 10 operations, like base 10 multiplication, base 10 addition, and so on, we will get the same value in base 10. Okay, if you didn't understand that, I think it's worth going back and just going back and seeing, just try to understand what I said before. Of course, remember, the difference between these online lectures and what we used to do before is that there was an interaction, right? I could write on the board, take questions, students could ask whatever's bothering them. But it's a bit more difficult now because I can't really, this is not an interactive session, right? It's pre-recorded. So what we would be doing in this case, in the online environment now, is post your questions on Moodle. Post your questions on the learning management system. In this case, the learning management system is Moodle, not Sakai, not Canvas. And try to invoke discussions. The tutors will also answer questions on the learning management system. So I'll also be able to. And if you do this, you can try to create your own environment for learning in this online environment because it's very difficult. It's very different from what I'm used to as well. I've been doing this for a while now, and I really enjoy lectures. I enjoy the questions because you never know what's going on in the student's mind. So it's always worth asking questions. In the online environment, it's much more difficult to actually diagnose what exactly the problem is in the learning. So, okay, great. So this is positional notation. This is the formula, the positional notation formula, and we can use this to convert any base to base 10 using base 10 operations such as multiplication, addition, and so on in base 10. Okay. So can you show that this representation is always unique? Yes, because no matter what the base is, if you put it in this positional notation formula with those base operations, you'll always get the same value. And so you can show that it is unique. So now we come to the heart of what we were talking about, or the heart of where we're going in this lecture slides, and that is binary numbers. So binary numbers are simply your binary numbers is simply the numbers 0 and 1 and the configurations you can get from that. So by definition, any number, any way you arrange zeros and ones, it'll be a number in binary. So binary numbers is a number system where your base is 2. That means instead of having 10 symbols, instead of having 8 symbols, you have 2 symbols. This means that there are 2 digits 0 and 1. Again, you can ask why. Okay, well, why? That's depends on what you're talking about, right? So why do we use binary? Okay, that could be a question that we could ask. And this comes from the fact that in up to this point, we've been up to a point before, we've been using, if you read chapter 1, you'd know that we were using vacuum tubes to be able to represent high voltages and low voltages. But then since that time passed, we came up with transistors. And that was probably the greatest invention in computing, because that allowed us a reliable way of representing low and high volts frequencies. So the transistor, because it allowed for us to do this using some kind of semiconductor like silicon, we could actually have if we put a 1 in a transistor, that means a high voltage, out comes a low voltage. If we put a low voltage in the transistor, out comes a high voltage. This way of using the transistor allowed us to represent our high and low voltages reliably. And so we just assigned low voltages to 0 and high voltages to 1. And this is why we use base 2. Okay, that's why we use base 2. If our transistors facilitated 3 bases, we would probably use base 3. If our transistors facilitated and so on, you understand. Well, there's something exciting on the horizon. There is a field in physics called quantum physics. And Richard Feynman, very sarcastically, I don't even know what he was working on at the time when he said this, but he said that if you think you understand quantum computing, if you think you understand quantum physics, you don't understand quantum physics. Okay, quantum physics is the physics of the small. It has to do with the micro level. And the reason why he said this is because our intuition comes from or evolved from the macro world. That is the world of the big, where we are, right? We evolved in the plains and we evolved open fields, we moved around forests, our brains are used to the physics of the big. But quantum computing is the physics of the small. And in this physics of the small, sometimes an electron can be in 2 places at the same time. And we're not used to that because that doesn't happen in the physics of the big. And so the reason why Richard Feynman said this, if you think you understand quantum computing, you don't, quantum physics, you don't understand quantum physics, is because our intuition, what we think we understand about it, doesn't hold in that sphere. And so that's why we resort to a strong grasp on mathematics to guide us through the to guide us through the use, to guide us through our understanding of quantum computing. And the reason why this is an exciting field is because according to Moore's law, the more transistors we can fit in an integrated circuit, we can get better performance from our hardware. And Moore's law says that we can actually have every 2 years double the amount of transistors that we had before, which is fantastic. But the smaller the transistors become, the more they start threading on this physics of the small, and this is where things become complicated, because we now lose the reliability because of subtle disturbances. We lose the reliability of our transistors. So this is the simplified version of the story, and there is more things that you can read about this if you're interested. Okay, great. So let's get back to this binary number systems. I digress. We need to talk about, so this why question is very interesting, but it's a much larger debate that we can have. In quantum computing, we also, instead of having 2 states, we can have 4 states. All right, not 2 states. In which case we would be using base 4 instead of base 2. And some quantum computers can actually have 6 states and so on. So we will be using base 6 instead of base 2. And so on. All right. So let's open up this idea of binary numbers. So let's start with counting in binary. So you know how to count in base 10. Okay, let's count together. We can count together in base 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Let's now count in base 8. 0, 1, 2, 3, 4, 5, 6, 7. There is no 8 in base 8. So the next number will be 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. There is no 1, 8 in base 8. So the next number will be 2, 0, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 3, 0, 3, 1, 3, 2, 3, 3, and so on. Let's count in base 5. Base 5, okay, so it's 0, 1, 2, 3, 4, 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 2, 0, 2, 1, 2, 2, 2, 3, 2, 4, and so on. Let's count in base 3. Right, so that's 0, 1, 2. There is no 3, so the next number is 1, 0, 1, 1, 1, 2. The next number is, well, if it says 1, 2, then it will be 2, 0. So it will be 2, 1, 2, 2, 3, 0. Okay, then there isn't any 3, 0 because it's base 3. So the next number will be 1, 0, 0. Then it becomes 1, 0, 1, 1, 0, 2. Then it's 1, 1, 0, 1, 1, 1, 1, 1, 2. And then 1, 2, 0, and so on. So this is important because in base 3, there is no 3, but there is a 2. So let's now move to binary. And this is where students usually get confused, but I think as we move on, you'll find that this is not as difficult as it looks. So we start off 0, then 1. The next number, since there's no 2, is 1, 0, then 1, 1. Then the next number after that is 1, 0, 0, because there's no 1, 2. So then you have 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, it's just as you would if you in base 10, if you got 9, 9, 9, what will be the next number? Well, if you got 9, 9, 9, the next number will be 1, 0, 0, 0. So similarly, because we reach the end of the highest number in base 2, which is 1, 1, 1, the next number must be 1, 0, 0, 0. Then you get 1, 0, 0, 1, 1, 0, 1, 0, then 1, 0, 1, 1, then 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and then 1, 1, 1, 1. And just as you would if you were in base 10 and you got 9, 9, 9, 9, 9, then the next number will be 1, 0, 0, 0, 0, 0. Okay, so just in this base, if you get 1, 1, the next number after 1, 1, 1, 1, 1, 1, 1, 1, 1 would be 0. Oh, sorry, it would be 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, I hope that makes sense. So that's the intuition there. Okay, so okay, great. So let's ask ourselves again. We asked ourselves the same question before, but why does base 2 interest us so much? So in this particular case, because transistors allow us to represent very high voltage and low voltage very conveniently, very reliably, then this makes a very suitable base to represent everything in, because so it's kind of, we are driven by our hardware. If the hardware allows for it, we change our representation. The base 2 in this case, we use base 2 because of this reason. And if our quantum computing comes true for us, then we'll be using base 6 or base 9 or base 4, whatever the machine allows us to do. Obviously, what matters at the end of the day, the most important thing that matters to a computer scientist is time and space. So time is in how long does it take. So if you're using base 2 compared to another base, does the other base, does it produce faster results? Is it more reliable, and so on? And the other thing is space. How much of space does it take to represent something? So you might find that base 2, even though it looks very strange and it looks like it takes more space, the computation in base 2, doing addition and multiplication and everything else, is extremely simple. And you'll see that later on in the next lecture. So we've counted in other bases, but there are nicknames that we give certain bases. So for example, octal is just fancy for base 8. Hexadecimal is fancy for base 16. So let's count in base 8 again. Okay, so the digits in base 8 are then 0, 1, 2, 3, 4, 5, 6, 7. The next number will be 1, 0. Then 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 2, 0, 2, 1, 2, 2, and so on. And then you get hexadecimal. This is now base 16. Hexadecimal is fancy for base 16. And the digits in hexadecimal, remember, if base 10 has 10 digits and base 8 has 8 digits, then how many, if base 8 has 8 symbols, if base 10 has 10 symbols, then how many symbols are we going to have in hexadecimal? Well, we're going to need 6, because it's base, hexadecimal is base 16, we're going to need 16 symbols. So 16 symbols. Let's start counting. All right, but this time there isn't a number such as 10 in base 16. We need a symbol for it. So we're going to just use the alphabet. So we'll have 16 symbols altogether, and with the symbols where we don't have symbols, we'll use alphabets. Okay, so we've got symbols for 0 to 9, that's your usual, but there isn't another one after 9. So we need to make up one. So instead of making up one, let's just borrow the symbols from the alphabet. So we've got A as a symbol, B as a symbol, and so on. So let's count in hexadecimal. We start off with 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E, F. What's the next number? 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9, 1, A, 1, B, 1, C, 1, D, 1, E, 1, F. 2, 0, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 2, 8, 2, 9, 2, 8, 2, B, 2, C, 2, D, 2, E, 2, F. 3, 0. 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 3, 7, 3, 8, 3, 9, 3, A, 3, B, 3, C, 3, D, 3, E, 3, F, 4, 0. 4, 0, 4, 1, and so on. You understand. And we're counting in base 16, which is hexadecimal. So let's put these base systems together and see what we get. So here we have binary with octal and decimal. And you can obviously add your other base systems in if you want to. You can have base 3 here, base 6, base 19, whatever you want. And let's compare, because when we compare, we can see what the conversions are. So we can see a binary in decimal, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Octal, 0, 1, 2, 3, 4, 5, 6, 7. 1, 0, 1, 1, 1, 2, 1, 3, and so on. Binary will be 0, 1. Okay, there's no 2, so it's 1, 0, 1, 1. 1, 0, 0, 1, 0, 1. 1, 1, 0, 1, 1, 1. 1, 0, 0, 0, 1, 0, 0, 1. 1, 0, 1, 0, 1, 0, 1, 1. 1, 1, 0, 0, 1, 1, 0, 1. 1, 1, 1, 0, 1, 1, 1, 1. And then what will be the next number? 1, 0, 0, 0, 0. That will be the next number. So if you write it out in this way, you can actually see the conversions. So you can see this number in binary is this number in octal. This number in binary is this number in decimal. This number in octal is this number in binary. This number in decimal is this number in binary, and so on. And some of you looking at this table must be thinking, I see a pattern. I see that every time for binary, okay, when there's the powers of 2, something happens, okay? So here's 2, you get, so in binary, we're looking at binary and decimal, right? So ignore octal. Okay, when you have a 2, you have 1, 0. When you have a 4, you have 1, 0, 0. When you have another power of 2, which is 8, you get 1, 0, 0, 0. And imagine what the next number would be, 16, which would be 1, 0, 0, 0, 0, and so on. So the powers of 2 have a special relationship with binary, as one would expect. If you think about it, it makes complete sense. But that's something for later. So, using your positional notation formula, as I told you before, you can use that to actually convert numbers from any base to base 10. So assume that this number is in base 2 and you want to convert it to base 10. How do you do it? All you got to do is simply take this number, you assume it's in base 2, and put it in the positional notation formula, and the result will give you the number in base 10. All right. So the question here says, take this number, assume it's in base 2, convert it to base 10. Then assume it's in base 8, convert it to base 10. Then assume it's in base 10, convert it to base 10. Assume it's in base 16, convert it to base 10. So how do you do it? Okay, well, let's look at the number 1010. So 1010. We look at this number and we see that if we assume that if it's in base 2, okay, then it must have the alphabet of base 2, which is zeros and ones. So that means there can't be any other number in here except for zeros or ones. And it is true. This could be a number in base 2 because all of the digits in here are either 0 or 1. So we can say, okay, it is possibly base 2. So let's check. We checked it for legitimacy in the 80s. So the next thing we need to do is apply the formula. So which formula am I talking about? Well, I'm going back to show you. I'm talking about this formula. This is the positional notation formula, this entire thing. So applying this formula, the positional notation formula, you have the number 1010 represented a base 2 number. You'll get 1 multiplied by 2, because that's the base we're in, to the power, all right, of, because this is position 4, right? Remember, all we do is we take the position and we minus 1. So because that's position 4, we are going to get r to the power of 3. Okay, I'll repeat it. 1 multiplied by 2 to the power of 3 plus 0 multiplied by 2 to the power of 2 plus 1 multiplied by 2 to the power of 1 plus 0 multiplied by 2 to the power of 0. And that will give you, if you put it in your calculator with base 10 operations, you'll get 10. If this was base 8, what would be different? Okay, all you're changing is the base. So it becomes 1 multiplied by 8 to the power of 3 plus 0 multiplied by 8 to the power of 2 plus 1 multiplied by 8 to the power of 1 plus 0 multiplied by 8 to the power of 0. Okay, if this is the base 10 number and you're converting it to 10, then there's no work to do, because as we remember from the thought problem that we spoke about, every number represented using the positional notation formula for that specific base will be the number itself. And so we don't need to even think about it. We know what the answer is. If it's a base 10 number, the positional notation formula will give us the same thing for the base 10 number. The same number. So 1010 is equal to, in base 10, is equal to 1010 in base 10. And it's unique. Finally, base 16, if we assume this is a base 16 number, which it can be since it contains digits which are in the range of 0 to F, then you can then say, well, it becomes 1 multiplied by 16 to the power of 3 plus 0 multiplied by 16 to the power of 2 plus 1 multiplied by 16 to the power of 1 plus 0 multiplied by 16 to the power of 0. And that will give you 4,112. All right, I hope this made sense. I hope this is easy to understand. So up to this point, you know how to represent any base, you know how to count in any base, and also you know how to convert from any base to base 10. All right, if you're given an integer in any base, you can convert it to base 10. So let's review what we spoke about, and we did speak about a lot of things. So the first thing I'd like to review is that we spoke about this dichotomy. Computers represent data in binary code, on or off, true or false, 0 or 1, high voltage, low voltage. And so because of transistors providing a reliable way to do this, we would like to represent numbers in such a format too. So we can represent numbers in any base. We are used to base 10, okay? I don't know why. They say it's a habit. They say it's because we have 10 fingers and 10 toes. They say it's because it depends on which culture you're talking about. But majority of the time, our influence has caused us to use base 10. This in no way is a limitation of mathematics. Okay, so in mathematics, you can represent any base, and you can do anything you can do in base 10, you can do in any other base. You can do addition in any other base. You can do multiplication in any base, subtraction and everything else. And you'll find that a computer, a CPU, is a glorified adding machine, because addition, everything that makes a computer special is simply addition. Everything. The data representation, everything that goes on in the CPU is addition. So yeah, that's pretty important to remember, because if I show you how to make an adder, you would know how to make a CPU, because that's all the CPU does. It's a glorified adding machine, a glorified calculator. Okay, great. So in no way is it driven by mathematics. Okay, and the point 4 is in base R, that's any base, the number, okay, if you represent a number, this is the leftmost digit, then the next digit after the leftmost digit, and so on. That just simply means in the same base you can represent the number using the positional notation formula. So by this point you should know that. And finally, the point 5 is that arithmetic works in any base exactly as it works in base 10. So there is absolutely nothing different. Obviously, the only difference there is that you are dealing with different number of symbols. And so you can have you shouldn't just smuggle in symbols. You should use, if it's base 4, you are only using 4 symbols. If it's base 5, you are only using the designated 5 symbols. If it's base 6, you are only using the specified 6 symbols, and so on.